Welcome back. Before we go on, I want to talk a little bit about one of the wonderful implications of Parseval's theorem. And that is, we found already with Parseval's theorem that if we're in a Hilbert space and we have vectors x and y, that we can take a projection and it's equivalent to an inner product. We take the inner product of x with y, and it's equal to the inner product of the L2 inner product of their coefficients, of their expansion coefficients. And the result of that was that if we take the inner product of a vector with itself, it's equal to the norm squared of that vector, which is equal to the L2 norm squared of the coefficients, projection coefficients. Okay, so that's what we're used to seeing, but look at this little application here. And that is, if we take the norm, as by Parseval's theorem, we know, or the norm of these two with respect to S, we know that we get this. We know that the squared norms are the same, so the norms themselves would be the same. And this is just the regular L2 norm. So why do we care? Well, you may wonder what happens if we mess with a signal in one domain, what happens to it in the other domain? It could be that we have some strange behavior going on where it's hypersensitive to what we do in one domain, and it shows up in the other domain looking very, very different. However, Parseval's theorem tells us that this is not the case. Basically, changing the value of an orthobasis expansion coefficient and it may not be clear yet. I'm going to explain how this relates to what I wrote above. By an amount epsilon, it will change the signal in a different way, but it will be by the same amount. Amount epsilon as measured in the other norm. All right, so that's in the S norm. Okay, so how does that happen? Well, let's assume that we took x. So x, and it transforms into alpha. How? We talked about that before, but I'll put it here just so that means that alpha sub k is equal to x with the k, excuse me, there we go, the kth coefficient, and then alpha is the vector containing the alpha sub k's. Okay, so we have this, and now let beta be a perturbed version of alpha. And one way we can do this is we could say, for example, beta sub k is equal to alpha sub k, except for one time, except beta sub j is equal to alpha sub j plus epsilon. And that holds true for k equals 1, 2, n, k does not equal j. Okay, so what we've said is we're just going to take the projection of x onto our ortho basis. We get alpha, the alpha vector. Alpha sub k is associated with the projection of x onto a particular basis vector vk. And now we're going to copy that, except we're going to mess up just one coefficient, the jth coefficient. We're going to add epsilon in there. So we just made a small change. We didn't really change much. What's going to happen to our original x? Well, so let's complete this story with y corresponds in the same way that x did to alpha corresponds to the vector beta. So once we have our beta, we can transform back. In other words, we can recreate y as a sum of the weighted basis vectors. They're all the same as we had before, except for the one of them. Now, if the universe is nice to us, making a small change in one domain is going to be a small change in another domain. Is that indeed the case? And yes, it is. Because of the equation above, which we got directly from Parseval's theorem, we can see that Parseval states that this our alpha minus beta, we know is just going to be it's going to be zeros everywhere. It's going to be the norm of a vector that just has one non-zero element, and this is the L2 norm. So it's the norm of epsilon times EJ, which is going to be epsilon. EJ would be the j indicator vector. In other words, it zeros everywhere except at j. And following through, we also know that this is equal to x minus y in S, which now we've just proven is epsilon. So if we have two vectors that are close in one space, they're close in another space. And we'll find this very useful going forward. Okay, so that's it for the magic applications of Parseval's theorem for today.